Hi, my name is Scott Simpson, and today we'll be talking about the harmonic oscillator as applied to quantum systems. So in this system, what we're going to try and do is actually have a function for our potential rather than a constant or just some numerical value. Like, for example, particle in a box, we kept our potential either 0 or an infinite amount. In the case of a finite wall, we just said it was some constant with some depth. This time, we're actually going to apply a function to it. So whenever we're considering oscillators, at least in classical physics, we fall back to Hooke's law, which relates the force occurring on that oscillator to a constant, and this constant's known as the force constant, and the displacement of that system. So F is our force. K is, if you're looking at a spring, would be a spring constant. This is known as the force constant. And then we have X, our displacement. However, we need this in terms of a potential because when we're considering the Schrodinger equation, we have the kinetic energy portion and the potential energy portion. So now we have to look or try and find a way to get the potential. So force is related to the potential energy. And we have the following relation to show that. Sorry, let me try to focus this thing a little better. It's still a little fuzzy. There we go. Where force is equal to negative dv dx. Now, what we want to try and do is separate these variables out and take an integral so we can get to this as a function. So if we take the integral of dv by itself, we'll just get v, the potential, which is what we want. So we got to split this guy up. We're going to move the negative sign over. Dx is equal to dv. Okay, now, if we, again, want to get this to a form where we get the potential out, what we need to do is add an integral. Oops. We add an integral to that system, and what we're going to get out on this side will be v. But we got to plug some stuff in here to see what we would solve for there. So what we're first going to do is move the negative sign out of that function. Then what we're going to do is plug in Hooke's law into this thing. So what will eventually happen is our negative signs will cancel out. And we're left over with kx dx. The other thing we can do, since k is a constant, we can pull that constant out. We're left with k integral of x dx. That's a pretty simple integral. We conduct or evaluate that integral, get k, well, we'll put 1/2 out front here, x squared. So 1/2 kx squared. So that's the function that we're going to be looking at. So if we consider a quantum particle that is in a function like this, or at least the potential follows a function like this, we're going to say that the particle is stuck in a harmonic oscillator or is in a harmonic potential. So if we consider a quantum particle in a harmonic potential, of course, this is in a 1D harmonic potential. We could plot it like this, where we have our potential, which is a function of x. We have our displacement, which is x. All right, so we have x and we have our displacement. And if you look at this function, or we plot this function out, it will look something like this, where each of these potentials is eventually going to reach infinity just because of the way that the potential is built, and we're applying the potential outside in this region. So our particle is trapped in this potential. The interesting thing is it can tunnel into this potential, which is something a classical particle couldn't do, but we can do it here. Okay, so the first question we're going to ask if we have a system like this is what would the Schrodinger equation look like? Okay, so to try and answer that, we should look at or start with the generic Schrodinger equation. Our Hamiltonian acting upon our wave function gets us the energy out in that wave function. Of course, the Hamiltonian can be broken apart into a kinetic energy portion and a potential energy portion. So let's do K hat, V hat, psi, E, psi. Okay. Now with that, we've seen the kinetic energy operator a lot since this system is only dependent on the displacement of x. We have that negative 2 h bar over 2 times the mass. Then the second derivative with respect to x, or the displacement. So this should be x up here. And then we have this function that we previously determined up here that we have to include as our potential. So 1/2 kx squared. And then that's all acting on psi, where psi we know is only a function of x. And that gets us E times psi of x. Okay, so that's what the generic Schrodinger equation looks like. But we have to figure out a couple of things in here and make this into a solvable differential equation before we can continue on.